Today, we are going to talk through the model assembly workflows or the connector workflows for 2023.1. We're just going to cover some high-level stuff in the slides, a couple of videos, and then load HyperMesh and go through some live examples from there. So the first thing we're going to cover today, so today's color mode is effectively what we've introduced. Historically, connectors had a mechanism in the browser that was quite hidden, and in the preferences to color the connector by things like connector groups and that sort of stuff. We've now migrated these options from the preferences and from in the browser to directly in the view bar at the bottom, alongside the face edit mode and the edge edit mode. So if we jump into the video, it's located just there. It allows the user to toggle between layer, state, style, control, and subsystem. So if you want to visualize the subsystem your connectors are in, or by control, you can visualize and see all the control styles applied to all of your connectors in the session. Show how to isolate by those different control styles. Again, so you can interactively change between them. And then if I change the type to layer, within the layer you can isolate by different layers, so 3T, 5T. This is dynamic, by the way, this legend. So if you have a 20T, it'll show that as well. And then state, which is the most common one, which is what we kind of default color by at the moment, which is state. This is far more direct and more accessible than what it used to be. Obviously, it's exactly the same place as where it was. And by default, the automatic mode is state, which is probably the most common and the most used. So the next thing we're going to cover, we're going to go through live demos, obviously at the end of this process. The next thing we're going to go through is the culmination of like it's been quite a long running release process that originally started with us working towards removing the postscripts, enabling us to do all of the logic and providing all the options that were available previously in hard-coded in the postscripts, directly available to the user in the connected controls. And now we're in a position that because we can effectively tune what used to be hard-coded and the differences, rather than having to implement 4 different connectors that were fundamentally the same with different parameters, one for various customers, we can now have one realization with a cohesive name that allows the users to exactly know what realization that they want, and then effectively tune that realization, whether it's property, material creation, and that sort of stuff, directly within the control itself. So what this should also address as well is one of the biggest criticisms we have of connectors to date is it feels like a very steep learning curve to use if you don't know what realization to use, and it's very complicated and can be very confusing. We really hope that this kind of steps towards cleaning that confusion and that sort of workflow down a bit. So what we used to see when we went to create a connector was, and this is a LS Dyna example, the 1,500 different realizations, but actually fundamentally all of these were duplicates and triplicates of each other. So what you should now see is a very simplified list. And in this case, for beam contact, the user can specify whether they want a MAP 100 or MAP 196 directly in the control. Historically, that card differential was the need for a different realization type. And now that's obviously embedded within the control and allows a far more easier understanding for users to say, what is the structure of the realization that I want, which is how we've fundamentally named our realizations now. And then what is the parameters I want to tune within that to get the exact realization style that they're looking for. What this actually looks like in process is there's a large number of realizations, and I can kind of got a couple of tables here that I'm not going to read through, but this is in our help. This is everywhere that kind of covers this So what used to be MAP 100 and MAP 196 and all of these realizations now have a consistent name. This is also consistent across solver profiles, which previously wasn't happening either. So you, for example, some of these are a mix of Abacus and LS Dyna and Radios. They all now have the same naming convention, and that also extends to things like Spring Rigid, which used to be Sealing Bush, RB3C Bush, RB3C Lass, C Bush Rigid. All of these are also now consolidated within Spring Rigid. The same thing for the line consolidation. We've also extended that same sort of process and that same logic. So again, what used to be hexaseam tie, adhesive contact, tapered T, hyper crash, glue spot sealer is now just hexa contact, because fundamentally that was the structure of the realization that the user was looking for. And then the tunability is now provided within the control. And you can even have things like, we've got the functionality for a user to specify text up front. So if they want a precursor to the naming convention, that's also available directly in the control as well. So things like seam quad, for the longest time, we've had angle plus cat plus this plus that plus whatever, and seam quad LTB. And then we get requests from customers saying, I need help with this particular type of realization. I'm looking for that, or whatever. And the truth was that the realization that they should probably be using was a different realization of seam quad LTB. So now we've really tried to push everything into one realization with one name, and the options allowing the user to really kind of tune what they want to do from that. Now the consolidation this consolidation project covers Nastran, OptiStruct, LS Dyna, Radios, and Abacus. And the last one I'm going to cover today is the solid bolt fasteners. So this is something that we have been requested for a very, very, very long time, and I'm very excited to finally be able to present this one. So solid bolt fasteners is one of the biggest use cases we keep getting asked for. So what we have here is the ability in HyperMesh via connectors to create solid bolts alongside with the pretension and the contact, all automatically created for you. So in this example, I'm going to automatically create bolt connectors. This isn't something particularly new, that one. I can take these connectors that we've generated during this process, assign the solid bolt control, and we can go into the details of the solid bolt, what's actually in those controls at the end of the presentation. We realize we've automatically generated, in this case, 10 solid bolts. If we review the pretension sections, we can see we've generated pretension. The pretension values can be defined within the connector control itself as well. So that's a tunable. We're generating a slip surface-to-surface head contact. In this case, in Abacus, it's a tie contact between the head of the bolt and as well as the shaft. The thread contact can be set to basically the entire length of the last link, or you can specify a thread length explicitly. Let's jump into the actual values on this. So I'm just going to do that generation that we showed in the video again. And if we jump into the control, we can see we've got that same control. Now I'm just going to expand this out a bit. We currently support 5 different pattern styles. So that's pattern 4. Actually, I'll just do it here. We've got pattern 1, which is a tapered bolt. We've got a tapered bolt with a washer head. We have a straight bolt with a washer head, and a double-sided bolt, effectively simulating a bolt and a nut for those use cases. Within each of these, there are tunable parameters, so a user can specify the different parameters applicable to each of the styles that they're going for. So I think we'll switch back to what we had before. I believe it was bolt 4. Diameter 2, so D2, which is the diameter of the shaft of the bolt, can be set to automatic. So that will take the minimum bolt hole size and automatically set the bolt diameter to that. Alternatively, you can set that to input. and the user can specify the diameter that they want explicitly themselves. You can specify the section of the where you want the pretension section to be specified with L5, as well as the mesh type. So in this case, you can specify hex or tet, and you can specify the mesh size you want for the bolt. For implicit solver interfaces and explicit solver interfaces, we allow the option for pretension with an initial stress value, and then for the implicit solver interfaces, you can specify a threaded shaft, a thread length, or you can specify tied, which just generally ties it to everything. And then you can also specify whether you want it to be the full length of the last part or a specific input value. For the explicit solver interfaces, we also allow, I believe, in LS Dyna only, but I will need to double check. Let me switch my solver interface to Dyna. Okay. For the explicit solver interfaces, let me just duplicate this. Create a new one. We allow a failing mechanism where you can specify a rupture material, and what that will do is it will generate the first layer under the washer bolt. Under the washer bolt, it'll specify a layer of material to allow you to have a failure mechanism embedded within that material, so a rupture material specifically for that. So once you've effectively defined the parameters of the bolt that you're interested in this case, we've got the different diameter values specified for the bolt heads, as well as the bolt length, initial stress section, that sort of stuff. We can then select the connectors, specify the control of interest, and realize it's fair. I'm in the wrong solver interface. Sorry about that. Switch that back to Abacus. But in this case, at least, you can see we've specified a directional force. We've got the magnitude applied directly from the connector control. If we review, we can see the loading to, in Abacus, it's got a slightly different mechanism. It loads to a node, and the node is associated to a node set. Is associated to a surface. So Abacus has got a slight quirk in there from that one. So if we actually review the pretension section here, you can see that there's a pretension section applied to the bolt through the center of the shaft. And that obviously that length there is definable within the control. So you can have it at the head, you can have it anywhere along the shaft length that you want. You just need to specify the appropriate value. In this case, if I come out of review, we'll turn off the bolt. You can see that there's the bolt pattern thread there. And that's taken, in this case, we specified it to automatic. So it's taken the minimum bolt size in that stack up and taken that for the diameter 2, which is the diameter through the length there. Turn everything back on. And then if we look at the contacts, just turn the geometry off. We can see that the contact is generated under the bolt head there as well to ensure that your bolt head's tightened. For anything more than a 2T stack up, in this case, we do not, we will manage the contact at the bolt of the head, we'll manage the contact at the thread, the contact in between the layers. The user will need to specify those themselves because that might be something specific to your setup. We also, if your final layer is a shell element, we will not generate a threaded contact. It has to be a tied contact, just because a threaded contact on a 2D shell doesn't necessarily, especially if it's a planar, like that classic 3-plate model, you're not necessarily going to see the contact in that case making much sense. So this is a super exciting one, this one, the solid bolt implementation. The solver profiles, I think I've covered this, but the solver profiles we've covered for this is Radios, LS Dyna, OptiStruct, and Abacus. For the Connector color mode, I'm just going to switch this out to a slightly different color. You'll notice as well, the 4 connectors, and maybe you won't have it yet, but zoom connectors will now zoom out. So if I show everything, connectors will now zoom out. So historically, if you zoomed out with connectors, you would end up with a very big green blob in the middle. That is now fixed in 2020. Come out of color mode. That is now fixed in 2023.1. So if you zoom out, connectors will zoom out appropriately. If you zoom in, they will zoom up to a certain size, and then they'll fix at that certain size. So in this case, we turn off this body side outer. We can see the connectors. We zoom in, they will get bigger to a certain size, and then they'll stop getting bigger. So this is all, again, just trying to reduce the impact from a visualization and a graphics point of view from the connectors perspective. So for the color mode, if we color by state, all of these are unrealized. So we're going to color by layer. You can isolate and see there's 6 connectors. The 6 connectors here that have failed because, or the 6 connectors here that have a single layer, and you should be able to interrogate from there. Are there, just jump out of that. We can jump to style and recolor by style. The style name obviously matches the style entry points in the ribbon. And recolor by control. The control, these are undefined, so I don't have a control associated to these in this particular model. And subsystem as well. So you should have a list of subsystems if associated, if realized, and dealing with multiple subsystems. So I'm just going to reopen a slightly different model. We're going to create a couple of connectors. I do not have my default file. That's okay. So in this case, you can see, and this is a good sort of segue into here, we've got that cut down list, the naming convention, everything is now organized. So I know that these are my heat affected zone connectors. This is my connectors with rigid. So in this case, if we go for this one, we can create another control here, and maybe a and everybody's favorite sim quad. Set that pitch to something meaningful for this model. Turn that off. Okay. So in this case, if I'm just going to create a couple of connectors here. And then I'm going to create some attachments. And maybe a line connector. Okay. So in this case, the color mode is by subsystem. So we can see here that the attachments are now colored as the same. So these attachments are colored by that subsystem. So if we change, I think if you change the subsystem color here, the whole subsystem changes, which is great. We can see that the rest of them up here, if we just do an isolate on those are all the subsystem connector subsystems. So that obviously translates through all of them. If we color by control, we can see the different control styles. In this case, if we come out of this mode and we can give them meaningful names, we can see those meaningful names here. So in this case, it's connector control 1. So we can just call this spot weld, for example, or rivet. MIG weld for this one. Come back into the color mode and color by control, we can see that those names are also reflected in the control. So a meaningful name here is quite useful to allow you to exclusively and specifically select the ones that are of interest to you. The color mode here follows very much the same process and the same kind of color legend that we have with all of the other face color modes and edge color modes. And again, layer just shows you how many links the connector, or how many layers the connector is specified for. Style is just obviously the general one across here, and then state, which is the most standard